I am Mr. Ish and I am welcoming you to this video, looking here and continuing with this concept of double integrals, utilizing double integrals for area determination procedures. If you have x squared plus y squared equals r squared, the unit circle equation you solve for y, which you see right there, this is what you end up, a semicircle. You know what the limits are, minus r comma 0 and r comma 0, because in all directions you're looking here at a radius from the center, which is the origin. That's what you have. If I want to determine the area of this, all of this, how can I do that? Well, I want to take this interval right here and I want to integrate it upwards across this interval right over here, that interval. You know we're going to be doing a double integral, but as we're moving up, we're not moving in a parallel manner, we're converging here towards the top. You have to account for that convergence, bidirectional convergence, so we have an extra complexity. How do we account for that fact? Well, we need to bring in an equation. What's the equation we have? It's right here, x squared plus y squared equals r squared, where we solve for y. But since we're going upwards in this direction, in the y-axis direction, you must solve this for x. X is equal to, you're gonna have r squared minus y squared. That's what you have. Remember, the base equation is x squared plus y squared equals r squared. The unit circle equation, anyhow, this is what we have. Now, how do we incorporate that in here? You've seen in the previous video, you bring that into the limits. Think about it. This right here is r comma 0 minus r comma 0. You're looking here at x comma y and minus x comma y. Technically, this right here is x. If you were to convert this into exactly what you see, this is what you have, r squared minus y squared in a radical, comma 0. And then you know what this would be. This would be minus square root r squared minus y squared, comma 0. This right here is your minus x comma y, and these right here are your limits. By bringing in this equation right here in the form of limits, you're going to get this convergence as you move upwards. Your integral will be this, minus square root r squared minus y squared, which is this right here. Remember, you're doing a to b with regards to dx, going up to this, square root of r squared minus y squared. This is my dx component. This right here factor will now integrate upwards with respect to dy along 0 and r. That's exactly how everything will play out. Focus right here on this inner integral. When you integrate this, you'll have an x, you'll have square root r squared minus y squared, and then here minus square root r squared minus y squared, upper limit, lower limit, the difference of the two, you'll have 2 square root r squared minus y squared. This right here will serve as the input for this integral dy. The 2 can come out as a constant, but you have 0 to r and this square root r squared minus y squared. This cannot be a constant or a coefficient out here because there's a y variable in it. You're doing integral with respect to y, therefore you must integrate it. Trigonometric substitution, a is equal to r, y is equal to r sine theta, dy is equal to r cosine theta, d theta. New integrals, theta 1 and theta 2, everything with respect to this, and 0 and r. 0 coming in there, you're going to get a 0. R coming in here, you'll have an arc sine of 1, which is pi over 2. Suddenly you've got this 0 to pi over 2, and you've seen this come. It's very common, coming in always with regards to integration of circular items, unit circle and all of that, it comes into play. You'll essentially have r squared minus r squared sine squared theta, and then r cosine theta d theta. When you play with all of this, you'll have an r cosine theta, which will multiply with that. In all of this area, by means of trigonometric identity, simplification, algebra, all of that, you'll end up with r squared cosine squared theta, which I'm bringing in right now. R squared cosine squared theta d theta. I want to bring the r squared outside and I want to bring a half angle or power reducing identity for here. You will have 2r squared 0 pi over 2. Remember, we're looking at the shaded area of this semicircle. If you were to use your traditional procedures, you know you'll have pi r squared over 2, half of a circle area. You do your top boundary curve minus your lower boundary curve from a minus r to an r with respect to dx, and you'd have pi r squared over 2, which makes sense. Half a circle is half an area. Power reducing identity for this, 1 plus cosine 2 theta over 2 d theta. You see this over 2, I'm bringing it out here and it'll cancel with this, but I'm going to remove it because we don't need to see it. it'll remove entirely with that. You can separate everything now across a positive sign. You will have r square 0 to pi over 2 d theta plus r square 0 to pi over 2 cosine 2 theta d theta. If you've done this enough, you know all of this will zero out, because when you do the u substitution, this will become r square over 2, this will become 0 to pi. If you do u is equal to 2 theta and then you use everything with regards to that, you will have here a sine antiderivative, sine of 0, and sine of your new limit pi will be all 0. It will zero out this r squared. This is all 0. Your only focus is now here. The antiderivative coming from here is a theta. You have an r square, and then you have pi over 2 and 0. You can just put the upper limit, and then the lower limit is irrelevant. You will have pi r square over 2, which is just what we wanted, the area of this, and it's good. Again, remember, we are integrating this horizontal interval, this integral, definite integral, the limits along the horizontal axis upwards with respect to dy. But you're not simply just transferring it up, because you need to account for this convergence towards this point. The only way you account for that convergence in an upward direction is the x equals square root r square minus y square formula, which then accounts for your ability to trace upwards in this circular manner. That equation comes in the form of your limits, which now reestablishes as your dx integral, which then integrates within your dy integral along its limits, and your double integral procedure comes to life. You solve it and you get pi r square over 2. That's what I'm showing you here. Thank you for watching, and stay tuned for more videos.